So could you see the screen? I think you can. So I'll start. As Ariana have just told us, I'm the first speaker, and I'm going to give the astrophysical perspective. Obviously, 15 minutes is not enough to give a proper review, and I'm not probably able to do it. So I'm going to share some biased views of the issue, basically. So I will start by talking about what astronomers think that matter is. What is dark matter for astronomers? This will be a very general view, which probably will be most useful for people who is not an astronomer. Then I will move on to talk about current searches for the nature of dark matter in astronomy in general terms, and then I will talk a little bit more in detail about one of the possibility of saying something about the nature of dark matter that had to do with the so-called core cast problem. And finally, I have a slide on where we went. Okay, so what is dark matter for the astronomers? First, I have to say that this is an old issue. Actually, it was posed in 1933 by Fritz Ricci. It's this guy in the picture, and it's probably, I mean, this is a not very well-known picture. It's the stuff of Caltech during a visit of Einstein, and the picture was taken at about the time where he proposed that dark matter was a fundamental constituent of the gravity of the universe. So, for those of you that don't know this guy, he's probably one of the brightest, if not the brighter, astrophysicists of the 19th century, of the 20th century, sorry. And but he at the same time was a bit arrogant, I would say, and not very politically correct. So this made that his idea took quite some time to be absorbed by the community. The basic idea that he posed have to do with clusters of galaxies. This is actually the common cluster that he used in the argumentation. So I'm going to use actually the discovery paper, so to say, to explain what he said. And I'm choosing it because it's really modern in the way it presents the problem. Okay, now basically says that in a cluster of galaxy, you can measure the proper motion, so the velocities of the individual galaxies. You have an idea of the mass they have, and assuming that the system is in some sort of stationary state, you should expect that the Bidial theorem holds, and so there should be a relation between the kinetic energy and the gravitational potential energy. So you know the number of galaxies in the Coma cluster of the order of 1,000, you know the typical masses, you know the typical sizes, and you can work out what is the gravitational energy. And so you can estimate what is the kinetic energy associated with this gravitational energy. And this kinetic energy has kind of RMS velocity associated of the order, if you do the numbers, of the order of 100 kilometers per second, which is one order of magnitude smaller than the dispersion of velocity that are associated. And so the conclusion is that there is a component that is not seen, but is determining the dynamics of the Coma cluster. That's what he said, and he even coined the name that we all use today for the dark matter. Now, I'm kind of usually reluctant to show this rotation curve, but I'm going to use it in other arguments. So I have to explain a little bit another typical observational result in astronomy that tells that dark matter is needed. Basically, if you have a galaxy like the one that you can see in the image of the background, and you manage to measure how the velocity of things like stars or gas move around the center of the galaxy, and if just assume that the system is in mechanical balance, the centrifugal force has to be balanced by the gravitational force. And this tells that if you have something that is concentrated and you are out of the center of the galaxy, the mass is constant, and you expect the circular velocity to drop down with radius and as a square root law. Now, if you go to real observations, you don't observe that thing. Actually, in this case, the circular velocity rises. So there should be extra mass that you don't see, and is producing this increase of the rotational velocity. At the same time, the fact that the system is in mechanical balance can be used to estimate the dynamical mass, also the dark matter mass that you have in the system. So if you manage to measure the circular velocity and the distance of the point to the center of the galaxy, then you have a handle on the total mass and so on the dark matter that is producing the velocity. So for astronomers, dark matter is the component that we don't see, but is needed to explain motion, basically. It's important to realize that it was originally an astronomical problem. So it was an hypothesis designed to explain an astronomical problem. And to some sense, it remains an astronomical problem if you include cosmology among the astronomical problems. Now, the paper by Zwicky is already of the order of 90 years old. And as it happened with the original paper, we still don't know the nature of the nature, but it has now passed to become one of the fundamental constituents of our cosmological model, the so-called lambda-cold dark matter. In this model, the dark matter that, as Ariana said, represents the 25% of the total mass energy of the universe, or 95% of the mass that is producing gravitational in the universe. This dark matter is assumed to be cold. So let me now move on to describe briefly current searches for the nature of dark matter within astronomy. Now, as I didn't say it, but it's something that is part of the common wisdom. The lambda-cold dark matter has been extremely successful as a model of the universe. It's able, with a few hypotheses and a couple of free parameters, to explain a lot of different observables. But at the same time, we already know that it's not the final word. So it's not the final cosmological model. It's not self-constrained. For instance, the cosmological constant is simply, if you try to work it out from first principles, it has a value, the one that is observed, that is the one that is required to explain the universe, which is completely off the estimates that we can make from first principles. So it's not the last word. So in a sense, we should expect to find tensions in the model. So observables that are not fully consistent. But this, rather than being a bad issue, actually allows us to say something that goes beyond the lambda-cold dark matter. In particular, if we manage to find tensions that are associated with the nature of dark matter, that's the way to go to say something about the nature of dark matter. Just to mention a few current tensions, the well-known Hubble constant tension. So depending on whether you can measure it locally or you can measure it at large scales, and the numbers of the Hubble constant, the expansion or rate of the universe is different, or is very similar, but slightly different. And these differences are inconsistent with the error bars that are put. So this is one of the tensions. There are another something similar that have to do with the clumpiness parameter. And among these tensions are the so-called small scale problems of the lambda CDM, which are the ones that I will focus on. And I will focus on because those are the ones that might easily tell us about the nature of dark matter. Basically, if we assume that the dark matter is cold, as that's the basic assumption of the lambda-cold dark matter, then you expect a very rich variety, by very rich spectrum of dark matter clumps being formed by gravity. However, well, this range go all the way from galaxy clusters to things which are smaller than the Earth. But if you try to see what happened with the clumpiness, at the scale of the order of 1 kilopascal, which is the size of the smallest galaxies, for you to have an idea in mind, then it's not clear that you see this clumpiness as is predicted by the cold dark matter. Now, this clumpiness can be erased basically in two ways. One is the feedback from the baryon physics, even if the baryons represents only 15% of the mass that is providing the gravity. In some cases, in some special parts of the universe, is able to actually feed back onto the dark matter and modify the gravitational potential that is produced by the dark matter. So it can erase these small scale features of that are predicted for the dark matter. That's one of the possibilities. The other possibility is that these small scale clumps that are expected from cold dark matter those are not simply not produced because the dark matter is not cold. And so it have to do with the nature of the dark matter. But if you really want to use this clumpiness or the lack of clumpiness to say something about the nature, you have to discard the fact that it's produced by barium feedbacks. And so this needs to be done through numerical simulations. Basically, you have to start with the initial conditions that are set by the CMB, by the cosmic microwave background, and let these small fluctuations to evolve to gravity and the rest of the processes, form galaxies as realistically as you can, and include feedback of baryons, include the physical effect produced by the baryons, and compare these with observations. Now, there are plenty of such simulations in the market. The consensus is that the large scale is given by any simulation. So it doesn't depend on whether or not you include baryons, and it doesn't depend on the nature of the dark matter. The large scale is kind of, I mean, it's the same, no matter what are the assumptions that are behind. However, when you go to scales of the order of galaxies, then things change. And this is just an example. This is two numerical simulations of dark matter. In the left, you see cold dark matter. In the right, you see self-interacting dark matter. The only thing I want you to notice is that it's very similar because the initial conditions are the same, but it's not identical. Actually, in the left, you see that the clumps are smaller, are more concentrated, and you simply have more clumps. So, so at these scales are the scales at which you can say something. Now, what are the problems or the tensions that can help us to say something about the nature of dark matter? I'm going to mention only two. There are many. And by the way, at the end of the view graphs, I'm not going to show them. That is a list of, I think of providing a list of reference and reviews where you can check and read the extra information if you are, I mean, if you are interested in going beyond what I'm going to say. So the first of these small scale problems is the so-called too big to fail. Basically, it says that if you make a model of a galaxy which is similar to the Milky Way in mass and other properties, of course, this is what is seen in the image to the right of the slide. Of course, you get the central concentration of dark matter, and then you find a lot of extra clumps that are supposed to be tracing the satellites of the Milky Way, but the concentration, the properties of these satellites are different from the properties of the satellites in the Milky Way. Here in the left, you see rotation curves for many of these satellites, and the dots are actual satellites of the Milky Way, and you see that the upper part is simply not covered. The problem basically is that this upper part is represented for the more massive clusters of dark matter, and of course there are mechanisms in which you can prevent dark matter halos from forming stars, but they will never affect very massive satellites, and so that's why it's called too big to fail. So these massive halos should have stars, but we don't see them. I mean, the halos that should have stars don't show them. Now, the second thing that I want to mention is...
Jorge, you have 3-4 minutes?
Well, yeah, maybe I will need 5, okay?
Maybe 5, but be warned.
Yeah, yeah. So the core cast problem is another of these small-scale problems of the lambda CDM. Basically, if you plot the density of one of these dark matter clumps as it varies with the radial position, if it is pure dark matter, cold dark matter, or pure cold dark matter, then your profile, your density profile should follow something close to what is called an aurora fring, and what which basically says that it keeps increasing towards the central parts. So this is a cast. Now, if you go to real galaxies and observe what happened in the inner regions of the galaxies, then you get a core, something that flattens up towards the central regions, and the difference is larger than the error bars, and so there's a problem. So how can you actually make the dark matter profiles to show a core rather than a cast as predicted by pure dark matter, cold dark matter simulation? Basically, as I said before, is the feedback of baryons can do that, or is the nature of the dark matter. It's not cold. So it's nature that is nature, it's dark matter that in a natural way produces the cause. In principle, I mean, you think, okay, so if we want to conclude that is the nature of dark matter or its baryons, we have to rely on numerical simulations, as I said at the beginning. And often these numerical simulations are uncertain because it depends on many super parameters that we don't fully control. But in the case of this course, it's clear that when you go to very low masses smaller than 10 to the 6 solar masses, so these are tiny little galaxies. Remember that the Milky Way is of the order of 10 to the 11 solar masses. These galaxies simply, the energy released by the stars that are forming these galaxies is simply insufficient to modify an Abraham Franklin Y and produce from the cusp a core. And so this is fairly model independent. And so if we manage to get rotation curves for low mass isolated galaxies, we might say something about the nature of the dark matter. And low mass means smaller than 10 to the 6 solar masses or so. There may be, this is a very tricky thing, and probably, I mean, people is trying to get those curves, and at the same time, it's at the limits of the present technology, so to say. Now, there's maybe a shortcut that has to do with the distribution of light, and we are working on that. And basically, the distribution of light in these very low masses always show a curve that is kind of indicative that maybe we can say something about the dark matter not being cold. And this is just a second to say that if you are an obvious way to go to infer properties of the unresolved structure of the dark matter halo is going through gravitational lenses. So the lens that is producing strong lens do depend on whether it has or not small scale structure. And so by proper modeling of the lens and studying in detail gravitational lenses, we could in the future say something about the clumpiness of the dark matter halos and so on the nature of the dark matter. And this is my last view. So I'm almost done. So it's basically, this is the message to be carried on to the next views, so to say. So I say that lambda cold dark matter is great as a model of universe, but it has tensions. It has tension because it cannot be the last model. It's good in a sense because we can study these tensions, in particular those that have to do with the nature of dark matter. And so we exploring, trying to understand this tension and trying to explain them, we can say something about the nature of dark matter. I mentioned the so-called small scale problem. And the tricky thing is to separate what is produced of this tension, what part of this tension is produced by the nature of dark matter, what part is produced by the feedback of the baryon. So whatever we say depends strongly on modeling. So this is critically important. And then we need additional information. In particular, I mentioned lensing, which is something that is going to be very important in the future, and the observed profiles of the mass distribution in extremely low mass galaxies below 10 to the 6 solar masses or so. And this in the near future could tell us something about the nature of dark matter, in particular, whether it is or not cold. So that's it, and I leave the floor for the next speaker. So thank you. Okay,
thank you very much, Jorge, for this nice and careful review of astrophysics issue in dark matter. I think it's now the time of listening the point of view of Maria Luisa, our particle physicist. So Maria Luisa, if you can share your screen and unmute yourself.
Okay.
I don't know what happened. Try to unmute again.